The video that you're going to take a look at now is the way that we can calculate enthalpy theoretically. There are actually 3 different ways that you can calculate enthalpy. Last year, I know for sure you all learned bond energies. I'm not sure if anybody learned Hess's law, and perhaps a few of you learned the enthalpy of formation, but we're going to go through all 3 of them in this video. All right, so starting with bond energies as a review from last year, this method makes 2 assumptions: that it requires energy to break apart all of the bonds that are holding the reactants together. And so since it requires energy, this is an endothermic process. And then we have to reform bonds of the products. And when a bond forms, energy is released. And so that is an exothermic process. So really, when you're looking at bond energies, it's a competition between how much energy goes in to break the bonds and how much energy you get out when bonds are formed. So really, you're taking a look at the difference. And most importantly, whichever involves more energy is going to dictate the sign. This this equation you can learn, but it's opposite of every other equation that you need to know. So I am going to suggest, rather than learning this one, because it's going to get you confused with everything else that we do, just think of it practically. Energy going in is positive, energy coming out is negative. Whichever one is bigger is going to have that sign. So I just think that's a safer way to do it than learning this equation that's written down here at the bottom of the screen. All right, so here's some examples of the average bond energies for things. Notice a few different things. Obviously, each bond is going to be a little bit different depending upon the size of the atoms and how tightly attracted they are and the electronegativities of the atoms and so on and so forth. I also want you to notice that for multiple bonds, as you go from a single carbon-carbon bond, 348, to a double bond, 614, to a triple bond, 839, obviously to break more than one pair of electrons apart, it's going to take more energy. So depending upon the kind of bond you have, different amounts of energy are required. All right, so here's a typical example for bond energy calculations. The hard part about this is you got to remember Lewis structure. So I know we haven't even done that yet this year, so you got to rely on what you learned way back when. But the order is just the way it is. We're doing this stuff first. So with bond energies, you got to figure out what kinds of bonds you have. So nitrogen's held together with a triple bond. We have only one of them. That bond is worth 494 kilojoules, so we have to input 494 kilojoules to break all the nitrogen apart. Hydrogen, you've got 3 hydrogen-hydrogen single bonds, each of them 435, so that's going to be a total of 1305. And then, so the energy going in is 2246. Then we get energy out to form bonds. We've got 6 NH single bonds, each at a value of 390. So coming out, we have 2340. So now just compare. 2246 going in, 2340 coming out. This is the negative side. This is the positive side. We've got more on the negative side. So delta H overall is going to be a negative 94 because of the difference. And it's going to be exothermic because it's got a negative sign. All right, some of the stuff that you have not seen before. Hess's law makes use of 2 important points. Number 1, there's a lot of enthalpies of reactions that are out there that have been measured, that have been recorded, that are trusted to be the appropriate values. Second, since enthalpy is a state function, remember that the process of getting from the beginning to the end is not what matters. It's only the starting and ending point. The pathway doesn't matter. So we can have the reaction take place in a single step, or we can have the reaction take place through a series of multiple steps, and it doesn't matter as long as you wind up in the same place in the end. So with that being said, Here's an example of a Hess's law problem. So you're given this chemical reaction, C2H4, reacting with H2 to produce C2H6. We need to figure out what the delta H is. Unfortunately, we don't have a whole lot of information about that reaction, but what we do have is information about all these other reactions. We know that this reaction involving the combustion of C2H4 produces 1411 kilojoules. We know that the combustion of ethane produces 1560 kilojoules. And then we know that the synthesis of liquid water from H2 and O2 gases gives you a release of 285.5 kilojoules. We are going to use these reactions, add them together because of the idea that it doesn't matter the pathway, it only matters how you end up. We're going to use these three reactions, add them together in various ways to come up with an overall reaction that you see here. So, couple things to keep in mind before we actually do it. You need to manipulate the equations so that the substances that are in your target equation wind up being on the right side of the equation that you're using. So for example, C2H4 is a reactant, so in this reaction I have it on the correct side. But C2H6 is a product, so I'm going to have to flip this reaction around. If you flip the reaction, you also have to flip the sign. So since I'm going to flip this equation, I'm going to make this a positive 1560. The other thing you have to remember is if you have to change a coefficient, so for example, this is a 2, I only have a 1 here, so I would technically need to cut this value in half since I'm going to cut the whole reaction itself in half. When you add the equations together, then once you have everything situated on the right side and with the right number of moles, when you add them together, you're going to cross out anything that appears on both sides of the reaction. If you remember, that's what we did with the spectator ions when we were writing net total and net ionic equations. We saw that sodium ions were exactly the same on both sides of the equation, so we could cancel those out. It's the same idea you're going to do with Hess's law. You're going to cancel out the things that appear on both sides of the equation. So, one more time to review. You're going to have to flip some equations in order to get the substances that are in the target equation on the right side. You're going to have to adjust numbers of moles, which means you're also going to have to adjust energy values. And you also need to add the equations together so that when you finally do cross out those redundant substances, you wind up with exactly the target equation you're looking for. All right, so let's take a look. So all I did was repeat, excuse me, what the last slide had. This is exactly what I gave you. But we already talked. What I'm going to do is, because I have two things here and I have two things here and only one here, I'm just going to double this one so that I have 2, 2, and 2, and then I can reduce later. It's going to be easier than having to cut 7 in half and deal with a fraction. So I'm going to double this one as opposed to take these two and cut them in half. Again, can you see that I've got 2 here, but I only need 1. I've got 2 here, I only need 1. I only have 1 here, but in order to combine them, I'm going to double this one so that ultimately I can just reduce it. All right, since I'm going to double it, that means my energy is going to go up to 2822. What else do I have to do? I have to flip this guy because I need C2H6 on the product side. So since I'm going to flip this equation, I'm going to change its sign. And this, I don't have to do anything with the H2 because it's on the right side. It's on the correct side, I should say. It's on the left side, technically. It's on the correct side, so I don't have to do anything with that third equation. So now I've got 2C2H6 plus a bunch of stuff. I've got 2C2H4, 2C2H6 on the correct side, and 2H2 on the correct side. So I'm going to add those together. So what do I wind up with? It's kind of weird. Why is this shifted down? Everything on the reactant side gets combined. So 6O2 plus 1O2 gives me 7O2s. And then everything on the product side, likewise, I've got 4 waters and 2 waters, so I get a total of 6 waters. Now I'm going to eliminate the spectator ions. So 7 oxygens on each side coming out, 4 CO2s on each side coming out, 6 waters coming out, and look what I'm left with. 2C2H4, 2H2 yields 2C2H6. So I've got, and then all I did was add these numbers up to give me that final value. So I added the negative 282, 2822, the positive 1560, and the negative 285.5. But this reaction is only half of what I need, or I'm sorry, is double of what I need for my target reaction. So I'm going to cut it in half, reduce it by 2. I get a target with a value of 773. All right, so there is an example of Hess's law. Third example we're going to do, enthalpy of formation. Running out of time for my video, so we're going to pause this and make a second video to go for to learn enthalpy of formation stuff.